All right, so we were finishing up getting this model for the temperature of an object in a cool room, and I was graphing it, and so I wanted in the last video, and so I wanted to kind of return to that graph and just show you what we've got here. This actually, I don't really like this picture. The fact because it looks like it's hard to see what this is actually approaching. So let me go to my window, and notice here my y-min is 0. I'm going to put my y-min at 0 so that we can actually see a better picture of what this function is getting close to. And that looks a little bit better because there you can see that it's not approaching 0, it's approaching something up here. And if I graph the line 69.55, and this is purely just to illustrate a point. I'm not going to like intersect this or anything, but see that that's approaching that line 69.55, that temperature, which is what we expect when we put something hot in a room that's of a lower temperature, that it'll approach the temperature of the room. Okay, so we have found our model, and if we go back to all this information here, we've got our regression. We did that. We got this PTD model, and then the way that I approached this was I actually immediately skipped down here and got t of x, right? If you recall. So I did the regression function, and then that was my PTD model, and then I added the 69.55 to it, which is what you see here. But I should point out that if you wanted to find the SSE, you would be finding the SSE of the regression before you did this. So it would be wise to calculate your regression first, and then you can change the function. I'm sorry, I said regression, to calculate the SSE first, and then you can change the function. But in terms of calculating the regression or calculating the SSE, it works the same as always. Use the same method as we did before. Okay. So let's go to actually using our model. So now we can answer some questions. Let's predict the water temperature at 50 minutes first. So that's just a vars y vars question. So we can directly input 50, and we get 82.76 degrees Fahrenheit. Now, if you had done this without adding the 69.55 back in, well, your answer would be wrong. Okay. Then to the nearest minute, when will the water temperature reach 80 degrees Fahrenheit? Okay, so that is a intersect question. So I'm going to put 80 degrees down here. And I know my window is already okay because I kind of designed it that way, but you might need to do zoom fit here. But Luke, I think I can just directly graph this, and we'll see the intersection. Barely got it there. There it is. And my intersection is 55.87 minutes, and we will round that to 56 minutes. All right, so that's an example of Newton's law of cooling. Why don't we look at another one? The temperature inside my freezer is minus 15 degrees Celsius, and the room temperature in my kitchen is a constant 20 degrees Celsius. One afternoon at 1 p.m. the power goes off and the freezer's internal temperature starts to rise. Find the model for the temperature T in degrees Celsius as a function of elapsed time in minutes. So this is different, isn't it? Because we actually, here we've got, here's the room, the kitchen, and we've got the freezer. That's completely illegible. That's supposed to say freezer is in the room, and it's heating up, right? Freezer's heating up. So this is not a cooling situation. This is a heating situation. However, it's going to work pretty much exactly the same, except that we have to make a few small alterations. So let's talk about that. So this, as you might expect, this is called Newton's law of heating. And in this case, we have an object that is put into a medium that is higher than the object temperature. And as you expect, the temperature of the object will gradually increase until it reaches the medium's temperature. Once again, we're going to look at the PTD, the positive temperature difference. And this is the thing that's different. This is the actual, just as for the law of cooling, the PTD is the thing that we can actually model as an exponential function. But the difference is that here we have to change the order, because since the object is cooler than the room, in order to keep this positive, we've got to do room minus object. Whereas before, so let me put heating. That's heating there. It's supposed to say heating. The heating PTD is room minus object, whereas the, kind of scroll back for a minute, where was it? Way back. The cooling PTD was object minus room. So cooling, object minus room, heating, room minus object. Okay. And as you can see, when we work this out, we first still have to get our regression function using, again, room minus object. And then we ultimately want to get the temperature of the object as a function. And so we solve for the object, which means that we would, algebraically, that we're going to add this to the other side and then subtract this from both sides. So that would end up with this being our, this is what we have to do to y1. So we get our y1 exponential regression function, and then we end up, and we go into y1 and we say, all right, we have to insert the room temperature and change it to a subtraction of the exponential regression function. So room minus exponential regression function. So let's do this with our temperature data for this freezer and see what it looks like. As before, I'm going to enter this off camera on my calculator now. Okay, so I just entered all this data in L1 and L2, and then as before, I need a PTD column, but be careful here because we're reversing the order of things in terms of, because it's heating rather than cooling. So my room is 20 degrees, so I want to do room minus L2. And that way we'll actually have a positive temperature difference rather than a negative temperature difference. So PTD, we want positive. So this is our data, and now we can do the regression. So go to stat, calc, 0, and then L1. Again, this is L3. Vars, yvars, function y1. And that is our PTD function. So let me go ahead. I want to go ahead and calculate the SSE of this before I start messing around with the y1. So I'm going to do that. I'm going to go ahead and calculate the SSE since it's easy enough to do. We just go to second stat, math, sum, second stat, resid squared, and there's our SSE, 0.0026. Okay. So there you see our SSE, and I'll bring the model back up. There's our mod. This is our PTD model. Is 34.999 times 0.95 to the t. So that's what you see right here. Okay. So then we could go ahead and calculate the average error in the same way as always. We could calculate our correlation coefficient. And then once you've done all that and you're done messing around with the PTD function, then we can go ahead and get the temperature model. And recall, like what I was saying in the previous slide, the temperature model, we're going to go to Y1 and we're going to insert the room temperature minus the regression function. So be careful when you're doing this, but we go to Y equals, and the room temperature was 20 degrees Celsius. So go to second insert, which is the delete key, which is always kind of scary. But see, now I'm on the insert function, and I'm going to type 20 minus. Okay. So now I have room minus the exponential regression function, and I've got the correct function entered for Y1, so I can actually calculate the temperature of the freezer at a given time, and so forth. And there's your actual freezer temperature function. So now we can answer some questions with this, like predict the freezer's temperature at 6 p.m. Remember that this, I think it was 1 p.m., right, when this went off? 1 p.m. one afternoon, yeah, so 5 hours later. 5 hours later, sorry about all the flipping around here. So now we can just do Y1 of 5. But this, remember, this is only after we've changed Y1. So we'll do Y1 of 5. And that's our temperature of the object after 5 hours, the object being the freezer. It's negative 7.29 degrees Celsius. And how long will it take it to get to 5 degrees Celsius when all your food's going to melt and be ruined? Well, that's a calc-intersect question. So we'll put 5 here, and for my window, this is in hours, so we probably don't need 120 hours. Let's do 24 and do zoom fit with that. I'm being a little bit fast and loose with that, but this will probably be okay. I forgot to change my my X-min. Not the best picture, but we can see the intersection. So there's the intersection. And my calculator estimates this to be 17.02 hours. So that was after 1 p.m., right? So what is that? 12 hours would be 1 a.m. and then another 5 plus, so that would be around 5 a.m. Well, apparently I can't do basic arithmetic. That would be 6:01 a.m. Sorry about that. Yeah, so 6:01 a.m. the next day. Our freezer will be at 5 degrees Celsius. Hopefully we will have done something about it by then and gotten our food out. Alright, so that'll be, I'll pause this video here.